Hey there, STEM Chemistry. This is Ms. Ruark. This is podcast 7.2, where we're going to be talking about phases of matter. Yeah. All right, so phases of matter. We know that both liquids and gases take the shapes of their containers. So if we were to fill a room with gas or even a cup with gas, it would fill up the container and it would take the shape of the container. But when we put a liquid into a glass, it takes the shape of the container, but it doesn't fill it. And we want to know what's so special about gases that makes them fill the container but liquids don't. So why? All right, well, the reason why is because of these things called intermolecular forces. And we haven't covered them just yet, but we will soon. And intermolecular forces are things that it's like a force of attraction. It's kind of like the bond that holds them together. Okay, so in an intermolecular forces, you have the particles in liquids and solids that stay closer together because the force of attraction between the opposite charges in the atoms is strong enough to keep them close together. However, in gases, you have this kinetic energy that's large enough that allows those molecules to overcome the intermolecular forces, and they can actually spread apart and be further apart from each other. Okay, so I've got pictures here. We've got our solid over here. It's nice and neat and ordered. Everything's close together. It's got some intermolecular forces that are holding them together. Well, here we increase the amount of energy that's in it. We increase the kinetic energy, and these particles are able to move freely around each other, but they're still close. Well, if we increase that energy some more, then you end up getting this gas that it's just total disorder. It's chaos. The particles are going anywhere they want to, and they're as far apart from each other as possible. All right, so this should be brand new. No, this should be review for you guys. So phase changes. You have different phase changes here. You have freezing, which goes from a liquid to a solid. You have condensation, which goes from a gas to a liquid. You have deposition, which goes from a gas directly to, here's deposition. I don't know if you've heard this one before. It goes from a gas directly to a solid. Deposition. All right, you also have dissolving, or dissolving would be where it's going from a solid to a liquid. Not freezing, melting, dissolving. Melting would be solid to a liquid. Now, dissolving, I can't really say. Dissolving, we can't really say that it's just solid to liquid. We're going back, sorry. And that's because on this one, you can actually dissolve a gas in a liquid. It might not stay there for long, but you can surely try to put it in there. All right, so dissolving is kind of weird. Vaporizing would be the same thing as evaporation, where it goes from a liquid to a gas. Vaporizing is when it happens with extreme heat, and evaporation is when it happens with low heat, and it just kind of happens on its own. And then sublimation or subliming is where it's going from a solid back to a gas. Sublimation. Okay, so hopefully you already knew this, but we're just kind of reviewing. Just remember that as you're going from a gas, where there's a lot of kinetic energy, to a solid, that it's actually going to release that energy. It's going to lower the kinetic energy. And as it goes from a solid to a gas, you have to increase that energy, which increases the kinetic energy of the molecules, which allows them to move around more freely. All right, so boiling. Let's talk about boiling. A lot of people think that water just boils, and that's just that. Okay, but actually, there's a couple steps to boiling. Okay, so the first of the steps is evaporation, which is when the liquid molecules at the top of the water actually just change into a gas. It occurs at the top of the liquid, right? And with evaporation, that's constantly happening right there at the top of the liquid anyways, without any heat being added to it. Well, as we increase that kinetic energy, we increase the temperature, the liquid will start to evaporate faster at the top of the water. And that's going, that kinetic energy is going to break those bonds that's holding those particles together. Well, as they change from liquid molecules into the gas phase, they create more water vapor, which is the gas, the gaseous water that's just above the surface of the liquid. Okay, and then when that vapor pressure that's just above the surface of the liquid is equal to the atmospheric pressure, the liquid will boil. Okay, and that's because the pressures are equal, and it allows those water molecules to just come straight up. Okay, and then so the temperature and the pressure combination here is what we call the boiling point. I bet you didn't know that, did you? All right, so you need to know this, okay? It's very important. Evaporation is something that just happens. It takes place at the surface of the liquid, but as we add more kinetic energy, we break the bonds between the particles. The liquid molecules change to the gas phase, which creates more water vapor above the surface of the liquid, and when there's vapor pressure and the atmospheric pressure is equal, it's boiling, and that is the boiling point, or the temperature at which something starts to boil. All right, so nature of solids. We have two different types of solids that we need to talk about. We have our crystalline solids and we have our amorphous solids. Okay, so a crystalline solid is something that's going to be nice and neat and pretty, and it's crystal in shape. Particles are going to be arranged very orderly. They're repeating. It's a three-dimensional pattern like a lattice. I think your gemstones, your minerals, your rocks, like your let's see, your garnets, your rubies, your amethysts, your sapphires, stuff like that. Those are examples of crystalline solids. They maintain their own shape. They have a very high melting point. They're typically going to be good conductors. And some more examples of those would be like your table salt, your granulated sugar, and even copper 2 sulfate. Okay. Now, on the other hand, you have your amorphous solids. These lack an ordered internal structure. Amorphous, meaning that morphing, they can change, right? So they're moldable. They can be formed into many shapes. You can melt them over a wide range of temperatures, so they have low, high, and medium melting points. They're typically going to be poor conductors of electricity and heat, and examples of this would be powdered sugar, glass, plastic, and wax. All right, so know the difference between the two because we're going to bring those back in. All right, phase diagrams. When we talk about the phases of states, then we have to talk about the phase diagram, and you need to be able to read the phase diagram. So it's based on the relationship between temperature and pressure. Temperature is always going to be on the x-axis here, and pressure will always be on the y-axis. Okay, and typically it's going to be the pressure will be measured in atmospheres and the temperature will be in degrees Celsius. You have to pay attention to the axes though, because sometimes they switch them and they put temperature here and they put pressure here. So make sure you pay attention. Okay. Okay. All right. So just looking at the states here, if we were to lower the pressure and increase the temperature, we would have a gas. So everything underneath this line is going to be a gas. If we were to up the pressure and lower the temperature, we would have to have a solid. And if we were to up both of them, we would be in the liquid phase. Okay, so your solids, your liquids, and your gases. And this shows the change going between them. We've already talked about those. There's a couple other things on here that we need to mention. Okay, so this first thing is this spot right here. Okay, this spot right here is what we call the triple point. Okay, and the triple point is where conditions are favorable for all three gases, or excuse me, all three states to coexist. Meaning to coexist, right? So they can all be present. The conditions are favorable for all of them to be there at the same time, the solid, liquid, and the gas. Okay, if we were to push the condition, if we were to, let's say, lower the temperature, it would push it towards the solid. If we were to lower the pressure, it would push it towards the gas. And if we were to just raise them up both a little bit, it would push it up into a liquid. So it's just kind of like that perfect spot where you can go in any three directions and you would get a different state. Okay, we also have, let's see, the line here that goes between the solid and the liquid. Ooh, I can't draw on it. Okay, this line here is what shows us, I have to erase that, that's really going to bug me. Sorry. Okay, that line there is going to show us the boiling point at any given temperature or pressure. So if we were to look here, and you'll have more lines you'll be able to read more information from it. But let's say that we were to go from here and we were to say, okay, well, if we have this pressure, what would be the boiling point of this, or not the boiling point, the melting point of this substance? And so we would come over here and say, okay, well, if we go straight down, we'll be able to tell the melting point or the freezing point, right? And you can do that for anywhere on this line. Well, if we wanted to know the boiling point, we would look at the difference between these. So if we said from here, all right, this is the pressure, what would be the boiling point? And then you'd be able to tell what the boiling point is. So that's the boiling point line and then the melting or freezing point line here. Okay. All right, and then this critical point here, this is the point where the pressure temperature line between the liquids and the gases kind of stops. Notice how the line doesn't keep going past that critical point, because that critical point there is the last point where you'll be able to have both the liquid and its vapor coexisting at the same time. It just kind of gets it's not favorable for the two to be coexisting. Okay, so the conditions for them, they kind of become identical, and you can't really tell. Okay, so the critical point, the triple point, make sure you understand the freezing / melting and the boiling point line. Oh, look, and that's it. All right, so we'll see you in class and we'll work on this. All right, see you then.